All right, so let's talk our way through transposes just quick. So first, a transpose is when you swap the rows for the columns. So what that means is that if I have a matrix A, my matrix A has columns, right? So it's got a first column and a second column and kind of on and on. Let's see. So if my matrix is, say, n by m, how many columns does it have?
Yeah.
That was m, right, Cody?
Yeah.
Okay. So I've got my m columns. How many entries do they each have?
N.
Yep. So the C's, right, are elements of R n. Is all on board with that? And really, I guess if I was doing good notation, I'd put an I here. Right, so all the columns are in Rn. Now, if I transpose this matrix, what I'm going to do is I'm going to make the columns rows and the rows columns. So my A transpose, and I'm really just defining this symbol right now, okay? And the transpose is going to be that I switch the rows for the columns. So what dimension is that matrix going to be? First, is it clear what I mean? Sorry, Jordan, go ahead. What did you say?
Are the columns now going to be in M dimensions and there's going to be N columns?
Good. There's going to be n columns and m rows because the columns, right? I'm taking a column vector like this and I'm swapping it into a row vector like that. So I'm going to have a C1 going across the top here. I'm going to have C2 going across here. And then on down to the bottom here where I'm going to have CM. You guys with me on that? So that new matrix is going to be a m by n matrix. Everybody on board with this? Okay. Now, and this is a crazy trick. What is the first thing that you notice about this? Given that one is n by m and the other one is m by n.
You can multiply those two?
Yeah. You can multiply these in either order, right? Why would you do that? Because you can. And so obviously we should. Right? So let's spend just a second thinking about that in the easiest possible case. I guess I should label the word. So if I was going to say this, I would say a transpose. You guys with me on that? All right. So let's try this out just real quick. I'm going to try this out with the simplest available matrix that makes any sense to do this with. So I'm going to go to the case of a vector. You guys with me on that? So I'm going to take a vector x. I'm just going to do this in the two-dimensional case just because. So here's a vector x, a times b. Or sorry, ab. Now, I'm going to be interested in taking this thing's transpose. So what is my vector's transpose going to be?
the row AB.
Okay. Okay, so often in books, you'll see that this thing is called a column vector. Sorry for my handwriting today, guys. That says column vector. This one then is called a row vector. And I should notice that this one is, what's the size of a column vector here? This guy is
2 by 1.
good. This guy is 2 by 1, and this guy is 1 by 2, right? Okay, so notice that there are two ways that I can multiply this thing together. You guys with me on that? So what are the two ways I can multiply this thing together?
You can do X transpose times X, or you could do X times X transpose.
Good. You guys with me on this? So I can either do the transpose times the vector, so the row vector times the column vector, or I can do the column vector times the row vector. What are the dimensions of each of those going to be?
Two by two and a 1 by 1.
Okay, which one's which?
The one on the left is a 2 by 2.
I think that one's a 1 by 1.
Yeah, so
Because
this,
the outsides of the the number by number, the outsides of that when you're multiplying is what is the new matrix.
Okay, yeah, that's right.
okay, so this thing is going to give me a 1 by 1 result, and this is going to give me a 2 by, oops, not 2 by 1, 2 by 2 result. Notice these are always going to be square. Even though the matrices I started with weren't necessarily square, this thing's always square, which actually is a property I'm going to rely on going forward here a little bit. You guys good with that so far? Okay. All right. Now, when I actually calculate this as a 1 by 1 vector, right, that's going to be my row vector AB times my column vector AB. What do I get out of that?
A squared plus B squared.
Yeah, you get A squared plus B squared as a 1 by 1 matrix. You guys see that? What is another name for a 1 by 1 matrix?
Is it
Scalar.
A scalar, yeah.
Yeah, it's a scalar. Wait a second. I just took a vector and dotted it with itself? Is that what just fucking happened here? Did that actually just happen? Did I just find another way to write down the dot product? Guys? Hello?
Yeah. Yes.
Yeah, this is just another way to write down the dot product. You guys see that? So this is the one-dimensional scalar x dotted with x, right, written as a matrix. So this is just another way to write down the dot product. So what I'm finding is that x transpose times x is actually just x dot x. This would be true if I wasn't talking about a vector x and itself, right? If I was talking about a vector x and a vector y. You guys see that? Now, this other one, is one we're not going to have much occasion to use here. Oops, I forgot to write this. Punchline. This is the dot product, right? Otherwise known as the inner product. This other one is called the outer product. It has some uses, but I'm not going to spend much time talking about it. I just want you to know that it exists. If we wanted to calculate it, how would we actually do that? So let's calculate 1, because I said we're not going to use this very often, but let's at least calculate 1. So x is a column vector, right? So I've got my column vector AB, and I want to multiply this by the row vector AB. So it's just the other order. And now things get a little weird because, well, I know I'm going to get a 2 by 2 result, but it feels weird to do the usual like pick up and drop ons, right? Maybe?
Kinda.
Kinda, yeah. So remember that another way you can characterize matrix multiplication, right, is you can take the matrix that you're multiplying in and then multiply it by the columns of the matrix you're multiplying by. So this is going to be a squared and ab and ab and b squared. And I guess really if I was doing a super good job, I would write this one as b times a. Are those different? Is that a thing I should be worried about?
No.
No, because multiplication is commutative.
Yeah, real number multiplication is commutative, so in this case it doesn't matter. I'm only highlighting that they're different. I'm only writing them differently here because we do deal a lot with matrix multiplication here. So I'm trying to highlight that maybe we should just assume it's not commutative, and then if it is, we'll relax afterwards. Does that thought process kind of make sense? That problem about not commutativity is also going to come up when I'm talking about transposing a matrix product. Oh, sorry. Let me label this. This is called an outer product. This will have less occasion to use, but it does exist. And again, you could do this with two vectors that were different. They don't have to be the same vector. Questions on those two? Okay, I'm gonna switch gears just slightly. I'm gonna bring down some Python code because what the hell? Oh, actually, I'm gonna do this. I'm gonna move my share to a different screen. All right, so since we know we can do this multiplication between A and A transpose, I want to fiddle around with this just a little bit. So I've got my kind of starting sketch here. I'm just going to comment everything out except for this part where I define a matrix A. So here's a matrix A. Right now this thing's square and it's 2 by 2, right? So I'm just going to make this a little bigger. Okay, so now this is going to be a 2 by 4 matrix, right? And I have some things that I can do. So one of the things I can do is I know there's a way to calculate the transpose here. So I'm just going to go grab that and bring it up here. Okay, so there's A transpose. And now what I'm interested in is the fact that I can multiply these two things together. So I'm going to store A transpose somewhere. So I'm just going to store it in a new variable that I'm going to call A transpose very creatively. And actually, I guess I'm going to be real lazy and call it A sub t. As far as Python goes, you can name your You can name your things anything you want as long as they don't start with a number, and as long as they're not a reserved word in the language. You guys shouldn't have any problems with this because you're just going to name them A and B and C like math students. All right, same thing. I guess I should print A sub T here. Okay, now what I'm interested in is displaying this kind of weird thing. So, quick question. How do you multiply again?
By adding numbers.
Don't overthink this. Go find...
By dot?
Yeah, we need to use the dot function. So just go find it. This is not a computer coding class, right? And so I'm not expecting you to be able to write anything. I just want you to know that you can copy and paste little code bits. So is it the matrix B that I want to multiply by here?
No, we need A underscore T.
Okay, so I put A underscore T here. Did that change what I'm multiplying?
No, you need to change it next line as well.
Yeah, so remember that this is just printing out text. So this is the spot where it actually needs to change. And keep in mind that the text you're printing out, or what's written in the little gray stuff, can lie. Right, so the little gray stuff doesn't get executed by the computer, and the person who wrote it may have been wrong, because the person who wrote it may have been you or me, and sometimes we're wrong. So don't take what's in the gray with some skepticism. That's weird. You guys see that? What happened that's weird? You guys see what happened that was weird? It happened again. You guys see this? Look at the shapes of these. Look at this. There's a 14 here and a 14 here. There's a 25 here and a 25 there. There's a -3 here and a -3 here. 17's here, 17. What the shit? That's real weird. Is that going to work all the time, or did I just pick a wackadoo matrix?
Nice.
Yeah, didn't you say like the outer product flips the matrix across a diagonal or something like that?
I said that transposing flips the matrix across the diagonal. Why are these the same when they're flipped? You guys see that? They're their own transposes? Dude, there might be something cool here. Okay, so let me switch back here. All right, so this motivates me to do something a little funky. I'm going to define a new word. So the new word I'm going to define is symmetric. So a matrix that got weird. How about a matrix A is symmetric if A transpose is A. You guys see why that we would call this symmetry? Does that make sense? It's like diagonal across the diagonal symmetric, right? So it's a mirror image across the diagonal. You guys all good with that? And now the weird thing that I've discovered is this, it seems like, so observation, A times A transpose is symmetric. So is A transpose times A. You guys with me on that? That's what it seems like.
Quick question about symmetric. Is it only symmetric about the bottom left to upper right diagonal, or is there a way for it to be the top left to the bottom right?
It is across the proper diagonal, so top left to bottom right, that it's symmetric. There probably is a definition for the other thing, which is, I would call that symmetric across the anti-diagonal. But I'm not aware that that appears in your book, and I'm also not aware of it being broadly interesting. But that could, it might be. I don't know. That happens.
Master's program?
My guess would be that it's a known thing that I've just forgotten. But it might be interesting. There may be entire textbooks written on the subject. I don't know. There are entire textbooks written about symmetric matrices. They are very handy. So this is an important definition. I think that we maybe should try to figure out why this is the case. And we're kind of out of time for the day, so I think I'm going to leave this to you guys as explore this a little bit. See if you can't find something interesting in the textbook that might help you demonstrate whether this is or isn't the case. I believe this argument is outlined in the textbook, so try not to read this exact argument, but it's after a bit of stuff. So you might be able to go through and find some nice information and then see if you can puzzle out why this is the case. I will tell you one thing, just a hint that you're going to want to get started, which is that A transposes transpose is going to be something. What do you get if you flip a matrix across the diagonal and then flip it back? Wait, if you flip it across the diagonal and then you flip it again, what do you probably come back to?
Your original matrix.
Yeah, it feels like one of these flip twice and get back where you started things. That is true. You might spend a second thinking about this kind of picture with columns from up here. Right, so if we swap the columns into rows, and then we take these columns and swap them into rows, that puts the columns back. You might want to like just double check that they don't end up like upside down or something. I think you're going to want to think about it for just a second. It's not quite as obvious as like 2 minuses make a plus, but it's not bad either. So Think that one through. And then the other question that you're going to want is AB transpose is something. And I'm going to let you guys fiddle with that a little bit because I don't want to take all the fun out of this subject. Is that cool? I do want to give you guys the... Did I switch? Which screen am I sharing right now? You guys are looking at OneNote, right? I do want to give you guys the impression that there is some mystery here. And so I don't want to just like explain all the everything. But if you guys are leaving class with way too many questions, feel free to reach out, okay? Anything else for the day? Okay. In that case, thank you all very much for coming to Zoom class today. You guys are really fantastic for sticking with this, and I really appreciate it. And yeah, good work.
Thank you, Joe.